Today we're going to have a pretty short video on activating and deactivating groups. What we want to ask ourselves is what happens when we already have a substituent on a benzene ring. For example, let's start with toluene. When you nitrate toluene, you have the choice of getting an ortho, meta, or para substituted derivative, and we want to know which one that we will get and why. So let's look at the intermediates that form when we treat benzene with the nitronium ion. So here's when we have the nitronium ion placed at the ortho position, the meta, and the para. And what I want you to pay attention to is where the positive charge is on the benzene ring. So let's imagine that we drew all of the resonance structures for this compound. We would get to the following three hybrids. In the first example, note that we've got a partial positive charge on the methyl group. And in the second case, we do not have a partial positive charge there. And in the third case, we do. So what this means is that in the first and second case, that we have a lower energy of activation to form them, and that these are going to lead to our major products. One takeaway message here is that whenever you have an electron donating group, you're going to have a preference for ortho and para functionalization, and we'll see that in the next example. Let's look at an ortho-para director, specifically anisole. We're going to draw the resonance hybrids of anisole as a neutral compound, and you can see that the negative charge is at the ortho and para positions. These are going to be the nucleophilic positions, and this is going to make anisole an ortho-para director. Whenever you see lone pairs that are on the atom adjacent to the benzene ring, so this gives you a general structure of X, where X could be any atom, and it has a lone pair, then this is going to be an ortho-para director. In this case of methoxy, then the group is also activating because you put more negative charge into the benzene ring, so this one is also an activator. And so this is going to be a molecule that reacts more easily and is functionalized at the ortho and para positions. And we'll see that in the next slide when we functionalize anisole with a nitro group, that we get the ortho and the para substituted groups as the major products, and the nitro group is only produced at 2% at the meta position. You might wonder, why is the para position favored over the ortho? That is because of steric effects. We have a slight steric effect of the methoxy group taking up space, so it's keeping the nitronium ion from accessing the benzene ring as easily, so we end up forming the para product as the preferred product. The larger the substituent that's on the benzene ring, the more para is preferred. We also have deactivating groups, such as the nitro group, and these increase the energy required to modify an aromatic ring because they take electron density away from that ring. We want electron density in the aromatic ring for it to serve as a nucleophile, but in every resonance structure that we draw for nitrobenzene, we have a positive charge in that benzene ring. Because the ring is partially positively charged, it's less nucleophilic, and the positions with partial positive charges are even less nucleophilic. So the nucleophilic positions on the benzene ring are the meta positions. So these deactivating groups, like the nitro groups, are meta directors. We can see this effect in the nitration of nitrobenzene. When we get the product distribution, it is 93% of the meta-substituted product, showing this great preference over ortho and para. But note that the reaction conditions here are more harsh, that we had to heat the reaction to 100 degrees C to get it to go to completion, and that's because of the nitro group being a deactivator of the benzene ring. Lastly, I want to talk about halogens. Halogens are ortho-para directing, but they are also deactivating. Why are they deactivating? That's because of the inductive effect. Why are they ortho-para directing? That's because of resonance delocalization. When we draw resonance structures of the bromobenzene ring, then we see that we get partial negative charges at the ortho and para positions. So those are the nucleophilic positions of bromobenzene. However, the bromine or chlorine or iodine is pulling electron density away from that ring, deactivating it. So we want to remember that it's ortho-para directing, but also deactivating. And that is all for today's short lecture.